Okay, that's nice. Oh, good morning. It's very nice to be able to give a talk here. So thanks for the organizers for inviting me, for giving me the chance to speak. Today I'm talking about Zeta functions and their applications in an area that now it's, well, I like it very much, and I think I can sell it to you too today, which is twisted conjugacy, which, as the name suggests, is just a generalization of usual conjugacy. Okay, so last week you learned about zeta functions, so I probably don't need to explain this to you, but I'll say it anyway. So Michael also gave the same examples as me yesterday. So if you have a group G, you might want to investigate some objects related to this group G. So you can just define a sequence, A and G, that encodes some information. And then the classical ones, you might want to count subgroups of a fixed index, maybe normal subgroups of a fixed index n, or maybe in my case, conjugacy classes, and then you group them by size, or maybe reducible representations, complex representations up to isomorphism, right? So I was working with the last two during my PhD, and then I learned about twisted conjugacy, and I don't know, I was very interested, and I was wondering if we can use zeta functions to tackle some problems. In twisted conjugacy, maybe you can use twisted conjugacy to get some uniform zeta functions, who knows? So I started investigating them. So as you probably know, the story is if you have that all these A and Gs, they are finite, you can define a Dirichlet series encoded as information. That's a zeta function. So you just take it as to be a complex variable. But then, as I mentioned, I'm interested in twisted conjugacy, so I should probably tell you what this is first. So twisted conjugacy is just a generalization of conjugacy in which we use an endomorphism or an automorphism to just twist a little bit. So basically you have a group G. I'm defining everything for automorphisms, but you could define this for endomorphisms as well. And then you define an action on G in which instead of saying that, well, you just take G acting on X, that's Gx phi of G to the minus 1. So, of course, if I take phi to be the identity, we recover usual conjugacy, right? And the orbits of this action, they are what we call the twisted conjugacy classes, or Haidameister classes, depending on who is working on this. So again, if you take phi to be the identity, we see immediately that that's just usual conjugacy. So you get the conjugacy classes. And when we're working with twisted conjugacy classes, one of the things that are more interesting for us, and I'll explain why in a minute, is what are the possible numbers we can get as Haidameister numbers. So if I take an endomorphism or an automorphism phi, how many classes does phi has? So how many phi twisted conjugacy classes are there? And that's called the Haidameister number of the automorphism or endomorphism. So a trivial example, if you take an abelian group, then we know that the Haidameister number of the identity is just the total number of conjugacy classes, so the class number, right? So the standard example, if you've seen a talk about twisted conjugacy, you probably have seen this example before. If you take Z, Z has precisely two automorphisms, identity and minus identity. So, well, we know that there are infinitely many conjugacy classes, so the Haidameister number of the identity is infinite. And if you take minus identity, so by definition, this is the set, well, the class of an element A is just the set of all elements of the form, well, elements that are twisted conjugated to A, right? So Z plus A minus, and then minus identity at Z. Of course, we see that that's A plus 2Z, meaning that if A is odd, this is the set of all odd numbers. If A is even, this is the set of all even numbers. So the Haidameister number of minus identity is 2. So here you have two automorphisms, two very different Hadamard numbers. And this is of interest, so knowing which numbers are possible. And for this reason, there is this concept that's called the Hadamard spectrum of a group. This is just the set of all possible Hadamard numbers. So if you take all automorphisms, which Hadamard numbers do you get? So for instance, in the previous example, we've seen that the Hadamard spectrum of Z is to infinity. If you take Zn for some n greater than n, then we actually get all possible numbers. It's not so hard to see. So you get all positive integers and infinity. And that's what we call full Hadamard spectrum, meaning that all values are there. Of course, this is very rare. Most groups don't have full Hadamard spectrum. But we see, okay, so we also have this concept of the extended Hadamard spectrum. So if you're interested in endomorphisms, as I am more generally than automorphisms, you can also define the extended Hadamard spectrum. It's the same story, but now it's the possible Hadamard numbers when you consider all endomorphisms instead of automorphisms. And then, as I said, it's very rare that groups will have this full Hadamard spectrum. Normally, they don't. There is actually one property that's more desirable for some reason. And that's what we call the R infinity property, or property R infinity. It means that every automorphism has infinitely many twisted conjugacy classes or Hadamard classes. Okay, so its Hadamard spectrum is just infinity. So there's been a quest for people to classify groups according to R infinity. So I'll give you some examples. I'll explain you why we care about R infinity. So one example would be Tabak and Wong. They show that bounds-like solitaire groups of this form, they all have R infinity. And well, many polycyclic groups were investigated. Many of them have R infinity, but not all of them. You can think of the infinite dihedral group that doesn't have R infinity, for instance. The free group of rank at least 2, of course, because Z doesn't have R infinity. The free group has R infinity as well. And well, Bleek, Feldstein, and Gonçalves, they showed that the Thompson's group F has R infinity. And more recently, other people have been showing that other Thompson's-like groups have R infinity. That includes Kushilokova and Gonçalves. They have a very nice work where they use sigma invariants to actually show R infinity. And some collaborators and I also showed for other types of Thompson's group that they have R infinity. So maybe it's worth mentioning that having R infinity, it might sound strange, but that's not inherited by subgroups. You can have a group that has R infinity and its subgroup doesn't, but you can also have a group that doesn't have R infinity and a subgroup that has it. Okay, so let me try to explain to you at least why we started this quest about classifying groups according to R infinity or even figuring out what their Hadamard spectrum is. So just paint the picture here. So basically, everything started with algebraic topology. In algebraic topology, well, in science, we care about fixed points, right? We want to know fixed points for many reasons. If you're applying for grants, you probably will explain fixed points have applications in economy, biology, and so on. But also in mathematics, we have good reasons to study fixed points. And if you have a homeomorphism of a compact connected, well, anyways, a topological space, you have a way of determining whether this topological space, this homeomorphism has fixed points using group theory through Hadamard numbers. So the story is more or less so far. You take the homeomorphism of your favorite, well, compact connected topological space. Then you get a lift. Universal cover, and you do something in there, and that's universal cover, and there's lift so that you get an automorphism of the fundamental group of that topological space. Now, if you have an automorphism of a group, you also have a Hadamard number, right? And then what happens here is that in fortunate cases, the Hadamard number of that group automorphism will give you information about the fixed point of F. So I'll give you one example. If you take, for instance, so this is not really one result by one person, but a concatenation of them. If you take a certain topological space, so M is a compact new manifold, maybe what you need to know from here is that its fundamental group is an impotent group, then having infinitely many Hadamard classes is equivalent to F being fixed point free, at least up to homotopy. Okay, so you can deform it continuously so that you get rid of all fixed points. But even, so in particular, if you know that this group has R infinity, you know that every homeomorphism will be at least homotopic to a fixed point free homeomorphism. But also, well, this is just one example of why we care, those unresolved equations, but like, actually, if you know that the Hadamard number is finite, this is a lower bound. For unfortunate cases, this is also a lower bound for the number of fixed points. So in that sense, it's useful to also know what the finite Hadamard numbers are. So just to give you some example of things we can do. So there's this result that I find nice because, well, we showed that things for submanifolds using purely group theoretical tools. So there was a result from Gonçalves and Wong where they showed that we can find a chain of closed submanifolds. In this case, there were new manifolds. They have increasing dimensions. And, well, if you take self-homeomorphisms, they're all fixed point free, at least up to homotopy. And they've chosen this manifolds so that their fundamental groups have polynomial growth. So that's basically because the fundamental groups were virtually nilpotent, but they wondered, is it possible to also build such a chain of manifolds that are not new manifolds, meaning their fundamental groups are solvable groups, but not nilpotent groups. They have increasing dimensions, and they are also fixed point free in a certain sense, so their homeomorphisms are fixed point free. And up to, I mean, that was 15 years ago, and up to, I don't know, now, we had a few examples, but they are all in dimension up to 4. And then Yuri and I, we actually found, we explicitly constructed not the manifolds, but the groups, the fundamental groups, and we know that there is a manifold associated to it that have exponential growth, and so completing, so to say, this result. Okay. Now, you probably don't care about fixed points of topological spaces, I guess. So maybe I'll tell you one reason in group theory why you do care about those. So Yabara, for instance, showed that if you have a group, for him, linear groups, linear and finitely generated group, and this group admits an automorphism that doesn't have R infinity. Well, it requires a bit more, right? It's not just not having R infinity, but this is an automorphism of finite order. But then we can tell that G is virtually soluble. So having R infinity or not might give you some information about the group. So for finite groups, for instance, we know that, well, that's just an easy application of the orbit stabilizer theorem. Phi is fixed point free if and only if the Hadamard number of phi is 1. Just apply the orbit stabilizer theorem to the identity element. But then Rowley showed that actually, if you have a group that's a finite group that admits a fixed point free automorphism, this group is soluble. So we could also rewrite this as having 1 in its Hadamard spectrum implies that G is soluble. So yeah, we have some connections with Hadamard numbers and group properties. Okay, so back to zeta functions. I learned about twisted conjugacy. I found it very interesting, and I wanted to see if it would be worth to work with zeta functions encoding twisted conjugacy classes instead of conjugacy classes. So as in my PhD, we had the problem. I'm interested in groups for which the sequence A and Z, say, is not necessarily finite. So for instance, if you define A and phi G to be the number of conjugacy classes, phi conjugacy classes, or Hadamard classes of size n, then Z, for instance, if you take the identity, you immediately have infinitely many. So you cannot really define a zeta function using that data. So instead, I considered taking the number of twisted conjugacy classes of the induced endomorphism on Z mod M, for instance. Now we have a finite group, and all those numbers are finite. But now we have a double sequence, so to say. So we define a bivariate zeta function out of it. So for Z, you're just defining, yeah? Yeah, sorry? Yeah. So this is the sequence of, yeah. So now, instead of just counting the number of conjugacy classes of, twisted conjugacy classes of Z, we are also taking the quotients. So you take, yeah, of course, then you have to take the induced endomorphism on the quotients. But it's for a fixed phi, yeah. Yeah, thanks. And then, because now we have two parameters, M and N, one counting the, well, one that's concerning the sizes of the classes, and one that's concerning the level, so to say, then we take two complex variables instead. We just define something very similar, but now we're divided by N2 S1, M2 S2. So of course, we don't want to define a zeta function just for Z. So the groups are mostly interested in our unipotent group schemes over Z. You can think of them as subgroups of the upper unitriangular matrices over Z. And then we can define more generally the bivariate zeta function just by taking the sequence C, M, and phi. So now you take the, so C and M is just the number of phi conjugacy classes of G, but then Z mod M over Z mod N. Just see this as a subgroup of the upper triangular matrices over Z mod M. And then just a remark, if we fix M and we sum over all the N's, then this means that we are summing, we are just taking the number of all twisted conjugacy classes of G over Z mod M of all sizes. So this is the same as the Hadamard number of this automorphism. Here I'm calling it phi M just to indicate that that's over G mod M. So if we make this specialization, I just set S1 to be 0, we actually get a univariate zeta function that counts Hadamard numbers. Now, I won't call this a Hadamard zeta function because this name is taken actually for different kind of zeta functions. So I'm just calling this a conjugacy class zeta function. Okay, so this zeta functions, so you know something about zeta function, so from last week. These zeta functions, they satisfy some of these properties that we would expect zeta functions to satisfy, right? So for instance, they have Euler decompositions. You can write them in terms of local zeta functions, products of local zeta functions, and that's very useful. Usually easier to make computations over there. And that also allows us to write the local factors in terms of p-adic integrals and so on. So just give you one example, just why not? So if you take the identity automorphism in Z, then of course, CIDPI, so let's just take the powers of P, so mod P. So we know that the number of identity, or well, just conjugacy classes, right, of Z mod P, J, Z, well, we know that this is an abelian group. We have as many conjugacy classes as the size of the group. So this is P to the power J, so the number of elements of the group. So we easily compute the zeta function of this one. So we just get, when we plug the Pj, we get a geometric series. We know how to compute this. So we just get a very nice factor, 1/1 minus P1 minus S2. And then the global zeta function is just the product of all these factors. Now we've seen that Z has precisely 2 automorphisms. So let us just, for fun, see what happens in minus identity. If we take minus identity, then we need to split in 2 cases because, well, we know that the class of an element A, in this case, will be given by A plus 2Z. So if P is a not prime, we know that multiplying by 2 is a bijection, so we get the whole class, the whole group. So you only have one class. But then if P is 2, we have something slightly different. Not a huge difference, but something happens. So if we consider first P to be a not prime, then we get that we have one class of full size, right? The full size of the group. And then again, we get, it's very easy to compute what this local factor is. Again, we get a geometric series. We get 1/1 minus P minus S1 minus S2. And then in the case of 2, the only thing that changes is that now we are multiplying by 2. So we have 2 classes instead of one represented by the, well, even, and the other one represented by the odd elements. So now we have 2 classes, and instead of having size P to the J, now they have P to the J minus 1 as size, size. So when we plug this into the zeta function, now we have a 2, and then just writing already 2, so 2 to the J minus 1, and so on. We get something that's actually very similar. You might not remember from previous slides, but that was precisely the denominator we had for general P, but we have this exceptional term, as I would like to call, which we would expect, right? We know that if you're inducing an automorphism to quotients, you might not induce the same type of endomorphisms on all quotients, and then that's where you get those terms. Okay, so when you compare, this is the zeta function of the identity and minus identity. They're very nice, but also Z is abelian. It can get very nasty, as you can imagine. Okay, but of course, I don't see what's the point of computing the zeta functions by hand. We actually need better techniques. And in fact, we can describe them in terms of p-adic integrals, which is nice, because then we know, well, we can read from these p-adic integrals that this is a rational function in certain parameters. And well, if we disregard these exceptional terms, then we also get some functional equation. That's not the case for the exceptional terms, but well, the meat of the zeta function will actually have nice functional equations. Yeah, it depends on phi. So yeah, for different phis, we have different primes that we work, like when you take the induced automorphism, you get something funny happening. Yeah. Okay. So I'm not computing an integral, but just to give you one example. So we can sometimes compute the integrals. So I'll just give you one example so that I gave you one non-abelian example at least. So we can compute if you take phi over the Heisenberg group, so the 3 by 3 upper triangular matrices, this is, we're taking the endomorphism that sends the generator, so this generator here to twice its value and then y to itself. Then we actually get some uniform, so well, maybe it's not uniform, I don't want to say, but we get the same formula for all primes in this case. Yeah, of course I picked the nice ones. It can get very nasty, actually. Sorry, this is a redundant one. Okay. Okay, so about the methodology, when you're trying to write this zeta function as an integral, what I'm actually doing is I'm sending everything to the Lie rings, linearizing the problem, and then I can actually count this. So I can actually give you the size of each twisted conjugacy class in terms of some linear system. So we get a matrix. So here I'm saying that it depends on the element G. Of course, it's log on the Lie ring. Like we get a matrix A phi of G. So that this A phi depends on phi, but also it depends on which element you're taking. And we know that one element belongs to the class of G if and only if well, the logarithm of height, so the correspondence of height into the Lie ring by the Lazard correspondence, you get that A phi G applied to that as a vector gives 0. So now it's easier to count, so to say, and that's quite standard for zeta functions, but that also brings an easier way to deal with Hadamard numbers for finite groups. Because the quotients are finite, right? And you might think that it's actually very easy to work with Hadamard numbers for finite groups because, well, how hard can it be, right? Finite groups. But it's actually very hard. Yeah? Yeah. No, yeah, you were right. Yeah, I missed that, yeah. So Peter Sanden, he was working on Hadamard spectrum and especially the extended Hadamard spectrum of certain groups, including finite groups, but also nilpotent groups, for instance. And one of his results was this one. So if you take Z mod Pn, then you could say that Hadamard spectrum is full in the sense that, of course, we only can have powers of P, but you get all of them, right? And he actually used some quite advanced techniques for that. But if you use this matrix that I mentioned before, we can actually recover his result quite easily. So we can actually just construct these matrices the way we want so that we get Hadamard number n. So we can actually do something that we want so that we get the divisor type of that matrix to give you as many solutions, as many elements in the solution like as you want. And then you can actually easily show that that's the case. You get one automorphism or endomorphism for each n. So it didn't spend much time on it yet. So his result holds for all primes in the case of the extended Hadamard spectrum, but only for P odd. So if that's also true for even P, I'm sure we can do it using these matrices, but I still haven't tried. So one consequence that we get is that the extended Hadamard spectrum of a finite abelian group is given by all elements that divide the order of the group. So if we can show something similar for P as well, we get the same result also for the actual Hadamard spectrum. I also mentioned that For finite groups, an endomorphism is fixed point it's fixed point free if and only if its Hadamard number is 1. And in that sense, this matrix also helps a lot because, well, what it means for an element well, Hadamard number 1 means you only have one class. It means that every element has the whole group as its twisted conjugacy class, right? So in particular, I only need to look at the identity element, but this identity element gives me actually a matrix that only depends on the endomorphism or automorphism. So it's quite easy to figure out whether you can find such an automorphism that will have only one class or not. I mean, it gets, yeah. So it's usually, this matrix, it gets more complicated when you get higher nilpotency classes, but that's precisely because of the part that is dependent on the element. So if you take the identity 1, you don't have that anymore, so it's really quite easy. And yeah, I think I was speaking very fast, because that was actually what I wanted to say here. You told me so.